happens to the momentum when we do that? So in the lab frame, so the velocity of the observer, notation it's got 4 there, but velocity of the observer is 0 meters per second. The momentum of A was 3 times 4, which is 12. Actually, it's the momentum of A, momentum of the total momentum. So this was 4, -5. And so the momentum of A is 3 times 4, which is 12. Momentum of B is 6 times -5, or -30. And the total momentum is -18. That we've done before, just rewriting in a slightly different form. If the velocity of the observer is 4 meters per second, so the rest frame of the 3 kilogram mass, because its velocity is now 0. The other one, as we established,
-9.
so the momentum of A in this frame is
0.
Oh,
and the momentum of B,
-45. Hold on.
take 2.
45. No.
6 times 9 is
6
not
times
45.
9. Yeah.
6. Oh, that's multiplying by 5.
I was multiplying by 5 too, yeah.
-54. And so my total momentum is -54 Newton seconds. So my momentum changes if I'm in a different reference frame. However, in this new reference frame, momentum should still be, the momentum should still be conserved. And the kinetic energy will also be conserved because it's perfectly elastic. Let's go to the other tack. So instead of going 4 meters per second, hanging out with a 3 kilogram as we move, I'm going to go in the opposite direction. So -4 meters per second. What is the velocity of the 3 kilogram now?
8.
And the 6?
-1. So the momentum would be 24. And -6. And 18. Oh, wait a second. That's
All right. So it was not my plan to come up with the sort of reverse velocity so that the final solution is just picked it sort of at random. So what I want to do in this technique is I want to find the 0 momentum frame. I want to find out where my total momentum is 0. Because once you do that, it becomes incredibly simple. I'm going to do it the long way first, and then ask you to let me know where you've seen one of the numbers we're about to calculate, where you've seen it before. Trusting we'll remember what the solution is. So all I'm doing is I'm subtracting some value here, v. So what I'm going to do is my momentum, I want my total momentum to be 0. And so I'm going to take my mass times my velocity in this new frame, so that's 4 minus v. And I'm trying to find out how fast do I need to go to be in this 0 momentum frame, plus 6 times -5 minus v. And solve for v. So this tells me how fast the velocity of the observer, so that total momentum is 0. Just a math problem now, so 0 is equal to 12 minus 3v plus -30 minus 6v. So add those and pick them over. So I get 9v is equal to -18. What is the velocity? What is the observer's velocity to be in a 0 momentum frame?
-2.
Let's check it out. -2 meters per second. And so this becomes 4 minus -2, 6. That becomes 5, or -5 minus -2, which is -3. 18, -18. Dramatic pause for you to sort of ask questions or at least confirm that what I have on the board is not complete garbage.
Yeah, give me a second, hang on. Why isn't, wait, the velocity of B, is it not supposed to be -7?
Because you're subtracting -2.
Oh, wait, sorry, okay. Yeah, cause you're already moving in the negative direction, and then if this is, okay, yeah, that makes sense.
Okay. All right. So now at this point, I've shifted, so first off, let me see your notes here for a second, if you don't mind.
Yep.
This is today's.
Yeah.
I'm gonna get that one more. So we've actually seen this number before, within this context of within the context of these two masses. Obviously, Jacob had a huge hint at the point where I stopped looking. Where have we seen this -2 before?
Velocity final, some type of. I have -2 equals velocity, -2 meters per second equals velocity final in my notes.
And for what problem was that?
Is the perfectly inelastic problem.
Yes.
And this will always be the velocity of the perfectly inelastic collision.
Always?
In one, sorry, I shouldn't use always.
In the context of this problem?
In a one-dimensional perfectly elastic collision, the velocity of the observer to get into the zero momentum frame will be the velocity of the perfectly inelastic collision
Okay.
in the lap frame. There are a lot of times, if you look at old tests, where the first question they ask is, I've got these two masses heading towards each other, or with these certain initial velocities, what is the final velocity for the perfectly inelastic collision? And then I ask for the perfectly elastic collision following up, because you've already done the bulk of the work right there. Anna?
I don't 100% understand why we are subtracting V. It seems like each of those is being altered by the same amount, but why could it not be? I mean, I don't see why it has to be minus V. Like, couldn't it be plus V in theory? I mean, it would come up with a different number. I guess I just don't see the logic of that.
If you're doing, I'll answer by example first off. If I want to figure out how fast this is going in a different reference frame, I just picture myself, I pick the one that's going in the positive direction, and I picture myself going along with it. So if I'm going the same velocity as it is, it looks at rest to me. Just like all of you look at rest to me, even though all of us are on the earth that we're spinning around.
Right.
So if this is at rest to me, then I'm subtracting. I subtract how fast what my velocity needs to be.
Yeah.
So if I'm doing it to one, I gotta do it to all of them. It's gotta be the same transformation process. So if I subtract from this one, I gotta subtract from that one. Now, if you want to, you could put plus V there, plus V and plus V, you'd end up with a positive 2. And so you do plus V, you'd end up with a positive 2, and then you would then add. If you would do plus V, then you'll add 2 to both sides.
Okay.
Mathematically, it's legitimate.
Right, okay.
The physical meaning is slightly different.
I see. Thank you.
You said that this velocity should always be equal to the final velocity of a
Perfectly inelastic collision.
okay. And this velocity, is this concept always involving some observer? Like this velocity right here, the like -2, you said that's the velocity that somebody would have to be following to,
In order for the total momentum to be 0.
okay, gotcha. So, cause I wanted to write that down, how should I word it? Should it just be like, in order for total momentum to be 0?
So for P equals 0, velocity of the observer equals the velocity for one-dimensional problem, one-dimensional collision. And total momentum to be 0. Velocity of observer is the velocity of the perfectly inelastic collision.
Velocity final, right?
Yep. Now the easy part. What we're trying to do is figure out a situation where the total momentum is still 0 and the kinetic energy is exactly the same as it was before. Kinetic energy is based upon speed, not velocity. So if this is a +6 or a -6 or a +3 or a -3, you would get the exact same kinetic energy. My momentum is 0. When I worked it out before, I had this as positive and that as negative. Well, I could have had that negative and that positive and still get 0. So all I'm gonna do is just switch the signs of my two velocities. -6 and +3. My speeds are still the same for each object, so my kinetic energy does not change. My momentum is now -18 and +18, so my total is still 0. So I now have a velocity, this is in the 0 momentum frame. My velocity for the 3 kilogram mass is -6, and the velocity for the 6 kilogram mass is +3. The last step. I started in the lab frame, I shifted by subtracting -2 to get into the 0 momentum frame. I now have to get back to the lab frame, so I just reverse it. If I subtracted -2 to get out of the lab frame, I add -2 to get into the lab frame. This is the velocity of the 3 kilogram mass,
-8.
meters per second. And the velocity of the 6 kilogram mass final,
1 meter per second.
which I believe is what we had before. Just to give you an idea of the way that I generally, when I give these problems and I'm writing up a solution, first thing I need to do is come up with an answer. The way I generally write it is, I got my 3 and I got my 6 kilogram. So lab frame, I start out with 4 and -5. And then I shift to the 0 momentum frame. Now, I do have to do the work at some point to get the -2, but minus -2, minus -2. So I get -3 and 6. Collision. These just flip signs, and then I back out. This is still the 0 momentum frame. And then I back out to the lab frame by doing the opposite of what I did here, plus -2, plus -2, 1, and 8. And then I clean it up with units and circle what the right answer is. Conceptually, a little bit more difficult than the other ones, I believe. However, mathematically, I find this one the simplest.
I assume you meant -8 there.
I did mean -8. Thank you.
Yeah.
And then I start grading it and I realize, oh, I made a mistake, and then I correct it. Now, what technique are you supposed to use? Don't care. Pick one. Please do not mix and match. Biggest trouble comes from the students. The students who have the biggest issues are the ones who have two different techniques in their head, and suddenly they're doing a little bit of this one, a little bit of that one. It does not work well, I have found. Pick a technique, learn how to use it. Because as mentioned before, on Monday, there will be a perfectly inelastic, one-dimensional perfectly inelastic collision and a one-dimensional perfectly elastic collision on the test, on the last test. Questions at this point? All right, I'm gonna give one to you. And I recommend you pick the technique that seems the best one for you right now, one that feels right. And it'd be really nice if I have an example here with numbers that come out as whole numbers in the end. Oh, no, not that one. That's boring. So 4 to 110. Hopefully I'm writing down the ones that give you nice answers in the end. 4 kilograms going at 10 meters per second. And 8 kilograms. Going at 1 meter per second. And just for the sake of troubleshooting, just make it the right positive for everyone. Notice this time, they're both going in the same direction. For you Mad Max fans. So, work on this on your own right now. I'm going to pause the video because as exciting as no action is, people don't need to see it. Technique number 1, we have two equations. We have initial momentum equals final momentum. So it's 40 plus 8, 48 is equal to, using C and D from last time, is equal to 4C plus 8D. And then our kinetic energy equation, 1/2 times 4 times 10 squared, plus 1/2 times 8 times 1 squared, which was 208, yeah, 208, no, 204, equals 1/2 times 4 times C squared, plus 1/2 times 8 times D squared. So we have these two equations right there. Solve for C or D, plug into here, come out with an answer. If we're doing technique number 2, we have our momentum. This is K initial equals K final. Technique number 2, we still have our conservation of momentum issue there, or equation. So 48 equals 4C plus 8D. Yes, you can divide by 4 to simplify it. And our other equation is A minus C equals A minus B is equal to D minus C, there we go. Yeah, Brooke, your equation was a little bit off. I think you had A minus C equals,
Yeah, I did.
it'd be A plus C equals B plus B.
Right.
All right, and so the second equation would be 10 minus 1 is equal to D minus C. So you have these two equations solved. And the third technique, the perfectly inelastic collision solution, I have 48 units of momentum and times 12 V, V is equal to 4. And so we start out with 10 and 1, I shift into the zero momentum frame, subtract 4, so I have 6 and negative 3. They collide, negative 6 and 3, back out into the lab frame by adding 4. And so 7 meters per second and negative 2 meters per second. I strongly recommend that over the weekend, you have an answer here, try to work it out if you did not get it while you're sitting here. And in case someone hasn't told you, and it hasn't been on video a couple times, but there will be, I guarantee it, there will be a perfectly inelastic and a perfectly elastic one-dimensional collision on the final test. And with that, have a wonderful weekend. I'm glad all of you survived Veterans Day.